computer. Recording in progress. We are up and running. What's that? You can ask your question now. My atomic int thing. Oh, you want to have a particular slide in mind, don't you? All right. Okay, so it's slide 153 for chapter 3. This is the wrong course. There we go. Yes. My atomic int. Okay. So what this is doing, this is showing you the semantics, the basic behavior of how an atomic variable works, right? Um, so they're not really implemented as locks, but if they were, this is how you could imagine it. So if you just think about the kinds of things that we have learned so far, and you're looking at this, you can say, these are the kinds of things that locks do for you. And one of the things they have is they have get and set, of course, but they have get and increment, and this atomically adds to the value, right? That's all it's telling you. Does that make sense? Um, so what we were looking, the context that this came up in was we were discussing progress conditions and how to identify how they work. And if you're only programming with locks, right, the only thing you know how to do is program with locks, then you're stuck on the blocking column, right? So you need atomic variables to do things in the non-blocking side. And yes, I showed you how to implement an atomic in terms of a blocking thing, but that's just for semantics. The idea is if you do things with atomics, you can make them lock free or wait free. Correct. If you've got a while loop, then you are not wait free. That is definitely true because it, it could be. Um, so there's a question you have to ask yourself about the difference between lock free and blocking, one of the blocking ones. And the question you have to ask yourself is, if the other thread suddenly went belly up, it just disappeared, could your thread still make progress? Right? Now, what happens with a lock, right? If the other thread gets the lock, and while it's got the lock, it goes away, right? Then you can't make progress. There's just, no matter what you try to do, you can't do anything until that lock comes back. But if you're trying to do like a get and set operation, and you're in a while loop trying to make that happen, in principle, that can work without the other thread being there, right? Because it's not holding on to the resource. So it's at some point, I'm hoping to be able to show you snippets of code and say which progress condition applies to this. All right. I don't know that we quite have enough ground for me to effectively do that, but anyway, that's the context. So you need to know that atomics exist in order for wait free and lock free to really make sense. Okay. Yes, that is part of the definition. Wait free is what we're working with. Wait free is the definition. If I ask you whether something solves consensus and it uses a lock, the answer is no. Yes. Let me pull up those slides. So basic atomic memory, just regular memory, reads and writes, gives you consensus number one. Only one thread can decide between a set of threads. The number of threads that can make the decision is one. But if you've got other read, modify, write instructions, you can do other things. Any non-trivial read, modify, write instruction gives you consensus number 2, right? Um, you don't happen to have a slide number for me, do you? Yeah, most of it is trying to convince you that this is really all this stuff is really true. Consensus number starts around 83. So multiple assignment, that was fun. I think it's kind of cool, actually. What slide number did you say? All right. Uh, any non-trivial RMW object has consensus number at least 2. Either get and set or a commuting operation, right? And you remember what commuting operations we talked about? Add, addition. And what's this? Okay, all right. That's commuting. That's commuting. I get it. Okay. Yes. Right. Now the way that comes into an atomic, right, is you have uh get and add, say. And you can take two get and add instructions and call them in either order and you get the same result. Right? That's the basic concept with commuting there. Um, and so this is the proof that any non-trivial one can work because what happens is we start by proposing our value, then we do a get and mumble, where mumble is whatever our operation is. And then if it's equal to the original value, if the thing that comes back from that is the original value, then we won consensus. And if it isn't, then we lost consensus. Um, all right. And so we either commute or overwrite, and then we get consensus number 2. And that was all trying to convince you of that. And then we said that compare and set has infinite consensus. Um, so what operations do not commute? Well, sufficient division, if I do A over B or B over A, I mean, if I divide by A and then I divide by B, it's going to get the same thing. That is going to commute, right? If I do divide by 3 and divide by 2, I'm still wind up dividing by 6. Subtraction, it's the same thing. If I subtract 1 and I do that twice, I can't, subtract 1 and I subtract 2, I can't tell which order I did that, right? Subtraction and division and multiplication, these are all commuting operations. What's another operation I can do? Exponentiation. So sure. So if I had an operation that says square, right? Square and cube. Square and cube are going to commute, aren't they? It's going to wind up being to the 6th power. The exponents will just add. What other operations can I come up with? Either. Yeah, so printing is not something that changes the state. But you're right. I was looking for something that changes the state. So finding a square root, well, a root is just another power, right? But it would have to apply to a double probably to make any sense. What's another operation? Pretend you're computer scientists. What operations do computer scientists like? Modulus. Modulus. Does modulus commute? No. It gives you a remainder back, and depending on how you arrange it, you can definitely get. So let's say I start with. I'm just making this up here, so I don't know how it's going to work out. I'm going to I'm going to initialize a variable to 7, and I'm going to have two operations: modulus with 5 and modulus with 6. All right. If I do the modulus with 5 first, what do I get? 7 modulus 5 is 2. And if I now do 2 modulus 6, what am I going to get? 2. Okay, what if I do it the other way? I have 7 modulus 6. What do I get? And now if I do the modulus 5, what do I get? Yeah, it doesn't commute, right? I can tell what order those things happened in. So I can build at least consensus 3 with modulus. You have to sit down and scratch on the paper a while to figure out exactly which numbers to use and so on. But you can build consensus 3 with modulus because it doesn't commute, right? See, a third thread can tell which order the other two went in. Isn't modulus what? Yeah, and I don't think anybody has a read, modify, write modulus instruction. I don't think anybody built that hardware. But that's not the point, right? The point is, if you had such an operation, what would its consensus number be? Yeah, but sure, it's kind of a theoretical question because who would do that? I mean, what crazy person would do that? Why would you do that? So get an increment and get and set make perfect sense. There's lots of uses for that, right? And compare and set, this is obviously a very easily usable thing, but get and modulus? I mean, come on. That's just nuts. Get and modulus on it just for me. Thank you. All of them. Somebody had some consistency questions, I think. Yes, Aaron. Okay, well, let's go back and look at the examples we have. Before we do that, does anyone got any other consensus questions for me? Ryan. I don't know, are there? Infinite. No, they all write to the same place. There's one memory location, one register. It's right here. Look. Yes, they all write a different thing, but only one of them can succeed, right? Only one of them so they all try to call -1 to some number, but the hardware only lets one of them succeed. And it tells the one that succeeded that it succeeded. I mean, it could figure it out anyway by just looking at the value, I guess, right? Parents. Hmm. Sure, but the concept of weight free is a finite number of steps, and compare and set counts as a step. It's one step, right? So Reagan, compare and set. I don't. To me, this seems like the easiest thing because I've got a -1 to whatever my thread number is, and if I succeed, I win. What is it about what is it about the concept that's confusing? Okay, so the idea, I mean, just sort of conceptually, what we're trying to do is solve a consensus problem, right? We're all trying to propose a value. Because this one can work for however many threads I have, so long as that thread number can be stored in the register, this is going to work, right? So, okay, well, if you can think about what's weird about it, it might be maybe you can help explain it to the rest of us. All right, let's go back and look at chapter 3. And I'm kind of so I didn't make most of these slides, but all the little timelines at the end I did myself. So I'm proud of those. Took me a while to get that to work too. Let me go to the ones I did. Uh, it's not one of mine. Mine are later. I will trust you. Yeah. All right. Yes, that's how it works. 135. That's when mine start. I did these with SVG and converted them to pings and then pasted them in there. And I have a little SVG drawing framework. It's all in Python. All right. So let's look at this execution. And is it linearizable? First question. Is it linearizable? No. There's no way I can draw lines in those write statements and have that read come out the way it does. Is it sequentially consistent? No. So the only thing that I could do to try to make it sequentially consistent is slide this write two around. And no matter where I put it, it's not going to make anything better. But quiescently consistent, the concept is if I have a group of things that are overlapping, I can reorder them. And so this is quiescently consistent. Does that make sense, Barrett? Yep, 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 absolutely. Yep. No, the right is the value we're putting in the memory location. We only have one memory location, and we're going to write different values in it, and we need to read a one, which well, so I'm saying that I look if I run my code on my computer and I look at this, and this is what I get back. The question is, does if I get this, if this is what I see when I look at the trace, the log from my computer, the question is, does it make sense? And the answer is no, because I wrote a three. I could logic out. I mean, it looks like it should be a three. I could logic out maybe it's a two, but not a one, right? So if I yes, it's crazy. So it's not linearizable. It's not sequentially consistent. No, no, no. So linearizable and sequentially consistent are precisely defined terms. Reagan, yeah. I can switch them however I like. If they're all overlapping, I can switch them however I like. Okay, so there's three things that we have. We have linearizable, we have sequentially consistent, and we have quiescently consistent. Now, quiescently consistent says that if I have a group of things that are overlapping each other, right, like these three, I can rearrange them however I like. And if I'm allowed to do that, I can make this work. There is a right one there. Had that been a right five, then this would not be quiescently consistent either. Also, right, if there were gaps, right, if I spread these out such there was a gap, a little white gap between each of these rights, then it would not be quiescently consistent either. Okay. Yep. Yep. Because this is part of an overlapping thingamajig. That's a technical term. Yes. Yes. Now, sequential. All right. So sequential consistency says what I can do is with sequential consistency is I can treat these like beads on a string or like an abacus, right? If I want to take this green thing and slide it way down here, I can do that. Or if I want to slide it way down here, I can do that. If I want to take this yellow one and slide it over, or if I can slide them along the string. I just can't slide them on the same string through each other. Yeah. Well, yes. Well, each of these lines is a thread. Okay. So sequential consistency says I'm allowed to slide them around like bumper cars or an abacus or whatever works for you. All right. Quiescent consistency says I'm allowed to rearrange them if they overlap. And linearizable says I have to take the picture just as it is, but I can draw a line inside each of these and pretend the whole thing happened at that instant. Okay, so those are my three things. And so let's look at the next one. All right. What is this? Is it linearizable? No. We cannot draw lines anywhere such that this makes sense. Is it sequentially consistent? Yes, because I can take this 3 and I can slide it way the heck over here. And I can take this 2 and I can slide it way the heck over here, right? So this is sequentially consistent. Is it quiescently consistent? Yes. Okay. Wonderful. We're doing great. Is it linearizable? Well, no, we already said that. Yeah, I can make it be a 2 or a 3, but I can't get to the 1. Tristan. So this has to do with if you're debugging something and you're looking at traces in memory and you're trying to understand the behavior of your code and whether its execution is something you can reason about. And whether you will wind up in that exact situation in your life, I can't tell you. Right. But what I'm trying to do is give you a model for how you can understand a parallel program, because it's not like just a regular sequential program, right? And it's going to behave differently. Yeah, yes. Um, I'm sure there are more. I'm sure that somebody's come up with some other wrinkle on these and has some other wrinkle on some CPU. And some of these come about because like if I say in my code A plus equal 1 and B plus equal 2, right? The compiler might switch the order of those. And it believes that that's fine because you shouldn't be able to tell the difference if you're just looking at that thread, right? But when you're looking at a parallel program and those kind of things happen, it can be very confusing. And that's kind of where we get these sequential consistency kind of things, because each thread is trying to be consistent in itself. but together they might not be. All right. So how about this one? Is it linearizable? No. Is it sequentially consistent? Yes, we can definitely make that work. Is it quiescently consistent? No, it is not. Because I got that little gap right here that keeps you from doing it. Yeah, you could switch the two and the three, but it doesn't help. How about this one? Is this linearizable? Now, is it going to be sequentially consistent? Is it quiescently consistent? So the funny thing is, if it's linearizable, those other two things are automatically true because linearizable is just harder to get. If none of them overlap, then it's linearizable. That means that wherever you draw the lines, it's going to work. Yes, because wherever you where what because the order that it's in works, right? If I put gaps between all these things, then and I put then I'd have to put the one out here. Yeah, if it's linearizable, then I don't need to shuffle it around to make it work. It's already okay. Right. Even if these things are all separated, right, I can still say it's quiescently consistent if those things could happen in that order, right? The point is with the consistency is can the order happen, right? Is the order allowed to happen? And in this case, the only requirement is that I write a one before I read a one. Now, if it's a queue, right, I have to get them out in the order I put them in. So there's potentially more work to do in thinking about it. Okay, so this is all three. Um, all right. Hopefully that gives you an idea about how to do those kinds of problems. Yes, McKay. Hmm. Well, I really need your help a little bit. This one, this one, I think this one is linearizable. You can linearize it two ways. Is it this one? Because I had to read the one. In order to read the one, I have to write the one. Yeah, so there's a write one on the bottom, right? But this write one has to happen before the end of the read one. Otherwise, I can't read the one. All right. Who wants a cookie? My cousin made these. Uh, the I guess so. I think they're pretty good. Well, I'm only teaching this class. You could, yeah, you can take two if you want. I don't care. Yeah. You need one, Calvin? All right. You sure? Yeah, it's a gift before you get the heart. No, I recently, last week I was in Chicago, and anyway, I got cookies. All right. All right. Um, so any other questions that you have on consensus or consistency? I injured my knee. Yeah, somehow. Consensus or consistency? How ready are you to face a trial by fire? Oh, the the homework you mean? The Peterson lock tree? Oh. Right. So the idea is the whole purpose of that presentation is to try and convince you that that you can't build weight-free consensus without a read, modify, write instruction. So the idea is we imagine we have some arbitrary tree of decisions that we can make, and that at each point a move we can move one thread can move by either doing a read or a write, and that's going to lead it somewhere. And at the end of a finite size tree, we've got to get to a place where I have either a one or a zero on the node, right? I've got to get to a decision. And so logically it follows that somewhere in that tree there's a critical state such that if I do a read or a write, I crystallize that into a one or a zero. Okay. And then we built a table and we just sort of considered, can I do it with reads? And the answer obviously is no, because how can you change anything with a read? Um, and can we do it with a write to the same or different locations? And again, we were unable to do that. We were unable to see how you could use a write to make a decision that would take you from one to the other, right? So that was the whole thing that was about. That was just trying to show you um, that that can't be done, and that's the way the author of the slides tried to build that point. I feel like I might be able to make something. Oh, I might be able to make something that's different that brought that same home point better, but it's not easy to do. I've been contemplating how I might present it, but I haven't got something that works yet. But that's all that is. That's just to convince you that you really need consensus. Mm. You really need read, modify, write for consensus, rather. And the main reason I gave you cookies is because I don't want to eat them all. Yes. Yeah, you can find other people to consume cookies for you. That's my experience. Um, anyway, all right. Any other questions on this stuff? Yes, McKay. Well, compare and set is an example of a read, modify, write instruction. It's reading, it compares it to the expected value. If it's not the expected value, it changes it. That's the read, the modify, or the read. Yeah, the read and the write is there. It's yeah, there's so there are any instruction that both reads and writes the data, reads and writes a memory location atomically is an RMW. So so we're so a compare and set is one example. Get and increment is another example. A get and set is another example, right? They're reading, they're modifying the value, they're writing it back, and it all happens at once. Any non-trivial RMW instruction has a consensus number of at least two, right? Basic reads and writes have one. They're trivial ones. And they're just, just read and just write has one. And of course, they're not really an RMW. They're just either an R or W. But any non-trivial RMW is going to have a consensus number of at least two because of that get and mumble thing we saw. And but that's just a whole set of instructions. And if you look at a given CPU, it might have, many of these. By the way, I was told by this guy I met at supercomputing last year. He comes up to me and says, "Oh, we got a new RISC-V board. It says it just doesn't have any synchronization instructions." So that means if you want to write your code on there, you got to get out your old filter lock. But at least if somebody hands you a board like that and says, "Hey, there's no synchronization instruction on here," you know what you need to do. You need to get out your filter lock. You said, "Oh, was it in Brandt's class? Where is that?" What's that? Yeah. Uh, Look, it's a prototype. They're just experimenting. They're just trying to build things, right? It's clearly not it's not a product coming from IBM anytime soon, right? It's a development board that somebody made. And you can test certain things on it, but there are certain things you can't test on it. Yeah, I mean, it's just a research toy at best. Okay, next question. You ready to take your lumps? Yes, yes. Just take these questions. I could show you my homework solution if you want to see that. I've got that here. Yeah, there's my homework solution. Peterson pyramid, I called it. I'm sorry, I have not yet done your homeworks. I will do it. And I decided I'm not going to assign a homework until I've got this one graded. So, because I feel like I don't want to feel like I'm that far behind. This way, I'm not as far behind. I'm only behind one homework. Yeah, but I have a different standard for myself than perhaps your other professors have. No, I haven't. Well, I one time we had some other 4,700 courses that we did. I taught with a team on just intro to HPC kind of thing, but I haven't done that since, people I worked with packed up and moved to Germany. So I like, oh, better in what way? I like smaller classes where I can do things like give you the chance to come to my office and answer in person and get half credit. I can't do that with 100 students. I like the smaller classes. I like the more advanced material. I like that I don't fail as many people. Well, it could look, I can't control whether you guys pass or not, really. I mean, it's up to you. I try to make it easier, but there's only so much I can do, right? Okay. So so when we proved that you couldn't make a queue, if I understand what you're talking about, when we proved we couldn't make a queue that was weight free, right? We did it because we showed that that would allow you to implement a weight free, that would allow you to implement consensus. And we know you can't build consensus. So we said we couldn't build a weight free queue out of read write memory. And the way we did it is we built a consensus protocol using a weight free queue, a hypothetical weight free queue. And that counts as a disproof because we know we can't build consensus out of memory. Hmm. Well, the thing we did is first we took a queue. We said pretend we have a queue, pretend it's made out of read write memory, and pretend it's weight free, right? Then we then use that queue to solve consensus, which is a contradiction. It intentionally made no sense because I was leading to a contradiction. You ready? Everybody, who's not ready? Okay, I'm going to speak now or forever hold your peace. I now pronounce you students. Okay, good.